Okay, let's continue. Now we will see a bit of theory behind of the waves and electromagnetic waves and etc. Okay. Well, to see how wave properties manifest themselves, we can consider a motion of a tight string. So consider a string of guitar, which is okay. Consider string of guitar of length L. This is Y and this is X. And when you pluck the string of a guitar, it moves from side to side. It starts moving from side to side and generate a sound wave. Well, there are in fact two effects here. Two effects. One is the motion of string itself, which is a wave motion. String itself starts to oscillate. And the second is the change in air pressure generated by strings motion, which are the sound waves we hear. Well, the sound depends on the size of a string and amplitude of the sound wave depends on the displacement. Okay, now here in figure we have a string with the length of L and it oscillates and amplitudes of oscillations are given as the coordinate y, and the equation of motion of string is here in this case d squared y divided by dt squared, which is equal to t g over w multiplied d squared y over dx squared, or we can write instead of this we can write v squared. V is the speed here, or velocity, doesn't matter. V squared d squared y over dx squared. And this equation describes the motion of a string, and here t Here T is a tension of a string. Well, G is gravity acceleration. And W is the weight per unit length of the string. Weight per unit length. Or yes, weight per unit length. Okay, V is velocity, and V here is the velocity of propagation of the wave in the string. Okay, this equation is a scalar wave equation, and its solution is in the its solution is a function y which depends on x and t. The important point is that it defines the form of a wave equation. The function y, which is also displacement in this case, is both time dependent and space dependent. Here you can see is time dependent and depends on t and on x. Well, there there are other terms that may exist, but two terms above are essential, which is x and t. Okay, now let's do a bit of manipulations with the string equation or with the wave equation. So we said wave equation d squared y over dt squared is equal to t g over weight d square y over dx square, or v squared d squared y over dx square. This can be rewritten in the form if we move v here. We can write 1 over v square d squared y dt squared equal to d squared y dx squared, or better we can write d squared y over dx squared minus 1 over v square dt squared equals 0. So what is the solution of this equation? The solution of this equation can be obtained in a number of ways. We may solve it numerically, or we may solve it by separation of variables. However, the if we want to solve it, let's say theoretically or analytically, okay. Uh, we may introduce a new variable zeta, which is x minus vt, and a new variable eta, which is x plus vt. And if we substitute it, if we substitute these two variables in our equation and solve the equation, so we put both here, we will have a general solution of we will get general solution of x y, which depends on x and t, which is equal to the sum of functions g x minus vt plus function f of x plus vt, where the functions x and f are arbitrary functions which describe the shape of the wave. Depending on the functions g and f, we may uh, we may we may make we can make conclusion about the shape of the wave. For example, the functions g and f can be harmonic functions sine x minus vt and cosine x minus vt. Okay, now we may feel this solution better by means of taking a very long or infinite string. So let's say we are taking an infinite string. Now at a time t equals 0, we create a disturbance such as plucking the string, or better, in other words, if we take a string at this point and create a disturbance here at a time t, our string becomes in so will be in this form. And okay, at so remember time t0 is for the second figure. And if we draw, so this is x, this is y, this is y0, and is we can call initial condition. And at the time t, we introduce a disturbance. We create a disturbance. For in example, we made plucking the string at some point. So this gives a initial condition of where yx 0 is equal to some gx plus fx. And after some time, for example, after a time t1, well, when we introduce this disturbance, it will start to distribute in both directions. To the right, it will start to propagate in both directions, to the right and to the left. After some time, after time t1, when time is t1, or let me draw, and after so after some time, when time is t1, disturbances have moved to the right and to the left at a distance of v multiplied by t1. So, okay, this is the y-axis. This is the x-axis, and this distance and this distance, both, well, ideally both are equal. In my picture they are not, but they both are equal. V t1, this is also v t1, where the v is the speed of propagation and t1 is the time passed after the disturbances. Okay, the disturbances propagating in the positive and negative directions propagate away from the source, and these disturbances are called the disturbances which are propagating away from the source are called forward propagating waves. And so for a vector field such as an electric or magnetic field, so for a vector field, Here we wrote this equation for in order to describe the motion of a string, the oscillating motion of a string. And this equation for a vector field is a vector equation. I mean, 1 over v squared multiplied d squared a over d t squared is equal to d squared a over dx squared, or d squared a over dx squared minus 1 over v squared d squared a over dt squared is equal 0. So here the vector field A, here A stands for any of the vector fields. For example, A may be the electric field intensity, or A may be magnetic field intensity, and etc., or maybe magnetic flux density. And well, v is simply speed of propagation of the wave, and in this case in okay, sorry, I made a little mistake. In the vector fields, the direction of propagation is accepted as zeta, so that's why here will be d, please pay attention, dz squared and also dz squared, and the wave is assumed to propagate in the z direction. Okay, let's see one example about the application of wave equation. So, okay, let me copy this example after. So the problem is saying, show that the solution yxt, which is equal to 1 over 2 x minus vt squared plus x plus vt squared, is a solution to the scalar wave equation. So what was our scalar wave equation? Scalar wave equation was okay. A scalar wave equation was d square y over d t square equals to v square d squared y over dx squared. Here we are given the function y, and it is saying that we need to show that the solution y, okay, the function y is a solution for this wave equation. How do we proceed? We take y and put here and also here, and And in both cases, we calculate uh, twice a derivative. In the first case with respect to time, in the second case with respect to x. Okay, let's try to do this. What we have? We have d squared y over dt squared. This is the left hand side of our equation, which is equal d squared over dt squared multiplied by 1 over 2 x minus. Okay, let me move 1 over 2 out of the bracket because 1 over 2 is constant. 1 over 2 d squared over dt squared over function of x minus vt squared plus x plus vt squared. So if we take derivative with respect to time, what we get? We get minus 2vt multiplied okay x is equal to 1 over 2 d dx. We are taking one derivative and the sorry, not dx but t. We are taking one derivative, that's why the power 2 and 2 becomes 1. Here we have 2x minus vt multiplied minus vt minus 2 x minus vt multiplied by v. Yep. Yes. Plus the same 2x plus vt multiplied by v. Okay. What we get? Equals to 1 over 2 d dt of minus minus 2x multiplied by v plus 2x multiplied by v simplifies. There remains only plus 2v square t plus 2v squared t plus 4v squared t. And if we take derivative from this with respect to time, we get 4v squared, and 1 over 2 multiplied by 4 is 2v squared. Okay, the left hand side, which is here, is equal to 2v squared. Now we need to compute right hand side. Okay, we can put v square d square y over dx square, which is equal to v square d square dx square. Oh, okay, let me write in the new line equal v squared over 2 v squared over 2 d square over dx squared. So x minus vt squared, x minus vt squared plus x plus vt squared. Now, if we take one derivative with respect to x, what we get? V squared over 2 dx. What we get? 2x minus vt multiplied by 1. Okay, 2x minus vt plus again 2x plus vt. And what we get? V squared over 2 dx. There remains 2x plus 2x, 4x. And if we take derivative from the 4x with respect to x, we get 4. 4v squared over 2 is 2v squared. Okay. Now we computed the right-hand side of equation, which is here, and which is equal to 2v squared. And we can see that right-hand side and the left-hand side of equations are equal. And, okay, these are equal, and this function, which is given as y x t is equal 1 over 2 x minus vt square x plus vt square, can be a solution to the scalar wave equation. So, okay, this is the a very short introduction to the waves and to the wave equation. And in the next lessons, we will go deeper to the electromagnetic wave equations and its solutions. So, okay, so far, if you have questions, you may ask. Or if you don't have, we may
Ustaz,
here. Yeah.
uni ikkalasi tomonda bir xil chiqdi-yu.
Okay.
Alo.
Yes, we are.
Ikkala tomoni bir xil chiqdi. Endi bu to'lqinlar bir xil deganimi endi?
No. No. This is just the, okay, look. This is the wave equation, yep? Scalar wave equation. And we are given a function here, some generic function. And it is saying that show that this function is a solution to scalar wave equation. We just want to show that this is the solution to our wave equation.
Tushunarli.
That's it. Well, for now, we don't know about the shape and about the form of the wave. For now, we are not interested and we don't know yet. Actually, wave is one, which is given in this function. Wave is given in this function. Okay. So, any other questions?
Yo'q, bo'ldi. Menda yo'q boshqa qolganlarda bo'lmasa.
Okay, what about others? Okay, if no questions, we may stop here and tomorrow we will continue.
Hop, ustoz.